So Jan Stolarek is going to talk about some interesting work on bringing injective type families into GHC with Richard.
Okay, hello everyone. Can you hear me? Yeah? Yes, okay, good. I will start this presentation with a short example that demonstrates the problem that we are aiming to solve. Let's say we have a type family declared like this. It's a simple identity function defined over integers and bools. And we have a term-level identity function, which unlike the normal identity function, has its type signature defined in terms of our type family ID. And then let's say we want to call our term-level ID function by passing in an argument of type bool. And we reasonably expect that this code will work correctly. There seems to be nothing wrong with it. But unfortunately, GHC thinks otherwise. It will reject the code by saying that at the call site, it is unable to pass to match the expected argument that expected type that we've given in the type signature with the type of the actual argument that we've passed in, and this happens because, according to GHC, type variability is ambiguous. So the source of this problem is that at the call site, GHC expects to infer values of every type variable mentioned in the type signature. Now, why is GHC unable to handle this case? I mean, for us humans, all of this looks simple, right? We look at the definition of our type family. We see it's defined for Booleans. We see that if we pass in a Boolean argument to our term-level ID function, then obviously the value of the argument in the type signature of ID has to be a Boolean, right? We see that. And we conclude this by looking at the definition of our type family. We look at the right-hand side, and we see that there is only one way we could have arrived at a Boolean result, right? A Boolean argument. And the property that we use implicitly in this reasoning is injectivity, right? We see there's only one way to arrive at a given result. But up till now, GHC knew nothing about injectivity, and it refused to make guesses, and there was no way to solve this problem, for example, by giving a type signature. And so our solution here is introducing injective type families, that is allowing users to inform GHC that a given type family declaration is injective. And I sort of demonstrated one error message here on this slide. But another error message that you will often see with type families is this one, which looks a bit nonsense because it says that we couldn't match type IDT with IDT0 because type family may not be injective. How many of you have actually seen this error message? Okay, so we're not solving a contrived problem. That's good. Our contribution is, firstly, a backwards compatible extension to GHC's type family mechanism that allows user to annotate type families with injectivity information. Once we have the annotation, GHC verifies that the given type family equations actually match the annotation, and we provide proofs of soundness and completeness. And we also present how to use injectivity information during type inference. And finally, we also provide some comparison between injective type families and functional dependencies. I'll begin by formally stating what injectivity is. So a formal definition says that a function is nth injective, meaning it's injective in its nth argument, if the following implication holds, meaning if we have two sets of arguments and we apply a type family to these arguments and the result of the reduction is identical, then the respective injective arguments must have been identical as well. A useful intuition to think about injectivity is this, that a result of type family reduction uniquely determines the arguments that were used for the reduction. And this is the intuition I actually used in the example, right? I said that if the result was a Boolean, then the arguments must have been a Booleans as well. From the user's perspective, using injective type families is quite simple. User begins by writing type family head in a normal way, and now what we need is a way to name the result of type family call, and we do this with this new syntax, equals R, where R is a type variable name, and you can put a kind annotation on it if you want. And then we use syntax shamelessly stolen from functional dependencies to say that the result uniquely determines the arguments A and C, meaning type family F is injective in first and third argument. And then we write down the equations, right? And you can see here, for example, that equations 1 and 2 have identical right-hand sides, but nevertheless, first and third argument are still identical for both equations, thus they are uniquely determined by the right-hand side. And if we give such definition to GHC, GHC will accept it, and information about injectivity will be used during type inference. If we, however, add another equation, and this equation happens to violate the injectivity annotation, because here the first argument the function is no longer injective in the first argument, and GHC will reject this definition by saying that there are equations that conflict. For example, for these two equations, it is not true that injectivity property holds the way it was declared by the user. Okay? And this is basically everything user needs to know about injectivity. Everything else is going on under the hood in GHC. And the major contribution of our work, a major part of our work, was the algorithm for verifying these annotations. And so instead of pulling the algorithm out of thin air, I will walk you through a couple of examples that demonstrate properties that our algorithm should hold. Okay, simple one. Is this injective? Come on. It certainly looks injective because, for example, if the result of reducing f1 is an int, then the argument must have been a list of ints. If the result of reducing f1 is a boolean, then the argument must have been a list of booleans, right? That's rather obvious, but surprisingly, we have to reject the definition of f1. It's not injective. Now, consider this. Imagine you have a call that looks like this, and we perform the following operations. First, we instantiate the equation of our type family, and from that equation, we derive this equality. And now, from the definition of injectivity, if the results of reductions are identical, and if our type family would be injective, then the arguments could be declared equal as well. And we just derived that lists are equal to ints, and that's a disaster. The way we solve this problem is that we do not allow var-type variables to appear as the right-hand side. And some of you might object here by saying that f1 is not defined for integers, right? But unfortunately, in Haskell, this is okay. GHC will not complain about such type. It will simply not reduce it. But the truth is that, indeed, the problem here lies with the fact that f1 is not defined for some of the arguments. And for example, if we have a function that looks like this, that's a simple type level identity function, but it's also a very useful equation for closed type families where we can use it as a catch-all equation. And here everything is okay. We can accept f2 as injective. And so we loosen the previous restriction by saying that we actually will allow var-type variables as the right-hand side, assuming that all left-hand side patterns are just var-type variables, meaning there's no pattern matching. This is a sort of total equation. Okay, what about type families? Can we have type families in the right-hand side? Well, here, unfortunately, we have to reject the definition. For the reasons similar to the first example. If we have a call that looks like this, again, we instantiate the first equation to arrive at this equality, and from the injectivity property, we could derive this, which again is a disaster, right? And our first intuition about this was asking ourselves whether we should completely disallow having type families in the right-hand side. Luckily, this is not the case. We can actually allow type families in the right-hand side in some situations. Consider this, F4. If we know that the result of F4 is a list of booleans, for example, or a list of something, then we know that the first equation must have been used for the reduction. If we know that the result of reducing F4 is arrow from something to something, then we know that second equation must have been used for the reduction. And So here we see a situation where the outer structure of the right-hand sides is different. And therefore, we can actually accept F4 as injective if G and H are also injective. And if any of them is not injective, then we have to reject the definition. And therefore, our rule for the algorithm is that we do not allow calls to type families at the top level of the right-hand side, whereas the situation that we've seen in the previous example. However, if we have a situation like this, then there's a problem. G might be injective, H might be injective, but nevertheless, F5 might not be injective if the results of G and H overlap. And so far I have spoken about looking whether the right-hand sides are identical, but what I should have said instead is that we should check whether they unify. Except that classical unification fails us here, because if we ask whether the right-hand sides, that is the list of GA and list of HA unify, classical unification will say, no, they don't unify because there is no substitution that makes them equal. So what we need is a custom unification algorithm that considers, F5 is not injective, we need a custom unification algorithm that considers type family applications to unify with any type. And so, summing up all the requirements that we have, we say that a type family is n-injective if, firstly, for every equation that we have, the right-hand side is not a type family application, and if it is a bare type variable, then all left-hand side parents are also bare variables. And secondly, for every pair of equations, possibly identical equations, that is, we check the equation against itself also, we require that the pair of equations is pairwise and injective, and the definition of pairwise and injectivity says that pair of equations is pairwise and injective if either the right-hand sides do not unify at all, or if they unify with some substitution theta, possibly empty, then that substitution makes the injective arguments equal in their equations. And again, when talking about unification, I mean our custom unification algorithm that we call, it's a special variant of the unification algorithm that has the following properties. So firstly, it treats type family applications as possibly unifying with any type. Secondly, if it's asked to unify application of of the same injective type family, it looks under that application at the injective arguments. So if we have a type family F with some injective argument, and the algorithm is asked to unify FA with FB, the algorithm will actually attempt to unify A with B. And thirdly, and this is not discussed in the presentation, it's detailed in the paper, we do not find solutions that involve infinite types. And we call this a pre-unification algorithm because if we ask it to unify two types that cannot unify in any way, it will discover this. But if it encounters types that could possibly unify, for example, via type family reduction, it will discover some information about the unifying substitution, but not all of it. And so revisiting our example from the beginning of the presentation, if we put an annotation on our type family that looks like this, this code will be accepted. So that's one thing that can be done with our implementation. And by the way, the implementation is already merged into GHC master branch and will be available with the stable release of GHC. Though there are plans of extending it in the future. So for example, here I've demonstrated the case where we are solving some wanted constraints, but notice the change of the signature of ID. We may have a case where we have some given information that involves, that could be solved using injectivity, like this. Here we have ID defined as function from A to B, except that the context gives information that ID of A equals ID of B. And using injectivity information, we could deduce that A in fact equals B, and this definition can be accepted. This is not yet implemented. This requires extending GHC's intermediate language core and this will be done sometime in the future. And I mentioned functional dependencies. As it turned out during our work, there is a very big similarity between the two, between injective type families and functional dependencies. And this is discussed in the paper. I will not go into details here, but one thing I wanted to say is that at the moment, our implementation of injective type families is less powerful than functional dependencies. Classical, a very good example of this is a type level addition function. Here is the function defined using functional dependencies, where we declare that the first functional dependency declares that the arguments determine the result, and second functional dependency, the one in green, says that the result and the first argument determine the second argument, right? And we would like to be able to do the same thing with type families, but at the moment this is not possible. We call this generalized injectivity, and this is also something that's going to be implemented in the upcoming weeks. Okay, so summing up. There's more information in the paper. We have some real-life example. The one that I've shown you here is a simple toy example, but the paper discusses example that actually came up in the vector library. There's more details of using injectivity information for type inference. We discussed soundness and completeness with proofs, and we have both proofs, except the proof of soundness has a hole in it, meaning we were unable to prove everything. There is a small part that we as conjecture holds true, but we are unable to formalize it. And we discuss also injectivity in kinds. And so our current work includes extending core, implementing generalized injectivity, and hopefully generalized injectivity will lead us to full proof of soundness, but this is not yet 100% certain. Okay, thank you for your attention.
One, I don't know if it's a question or a comment, but this is, oh, is this better? Oh,
Yes, much better.
Is there, or maybe what is the relationship between closed type families and injective type families? Because I can see they're different, but I can also see how some of the things that at least I would immediately think of doing with injective type families I could do with closed type families.
Okay. No, you wouldn't. Meaning closed type families don't have sort of right to left reasoning. So, for example, if the example I've given you at the beginning, if you rewrote it to closed type families, it still wouldn't work. So that's one thing. The other thing is that there's a small lie here. The algorithm given here works for open type families, and for closed type families, we also have to account for the fact that the equations are ordered. Okay, it's a small twist. It doesn't change the overall idea that I've demonstrated here.
So, is there like a concrete thing or is there something I could see your graphs that would show me, oh, you can do this with injective type families and you want to do this, and it would be really hard or impossible to do it with closed type families?
No, I mean, this is an extension that adds to open type families, closed type families, and associated types. So not sure if this answers your question, meaning you can have a closed injective type family. That's not a problem.
Oh, okay. I can talk with you more.
What if you just wanted to add a new line for type instance in another module later for a type that didn't exist at the definition site?
Oh, that makes sense. Yeah, okay.
So currently you can have a type class with an associated type family and use the equal sign to provide a default implementation for that type family. This kind of co-opts the equal sign in some way, If you want to have an injective associated type family, then how do you distinguish an equal sign as signifying that it's providing default implementation as opposed to something that's signifying something that's supposed to be injective?
If I correctly understand the question, with open type families and closed type families, you can provide the name of the result type variable and skip the injectivity annotation if you don't want it. For associated types, if you want put an injectivity annotation, you have to add the part with the bar and the dependency between the variables. If you write an associated type and then equals something, then this is associated type default. So they are distinguished by putting a bar and the rest of the annotation.
Okay.
Again, discussed in the paper. Yes.
Thank you.
So, could you say more about the additions to core that you envisage would be necessary to simplify givens as well as improve wanteds?
We have to add coercion that will decompose type families on the injective type families to get to the injective arguments. I'm not sure if this answers your question.
So what I'm wondering is whether if you can construct inverse functions, then you avoid needing to extend core, and instead can actually sort of make available the fact that a type family is injective as providing an inverse.
Honestly speaking, I don't know. I have to think more about this. Okay.
Thank you.
Thank you. Let's thank the speaker again.